and welcome to another episode of the Data Science Decoded podcast. It's good to see you guys. Hi Neil, hi Mike, how are you today?
Never better.
Yeah, we're okay. I'm glad to see you. And let's start talking
Happy
about.
with the results of the elections, or are we in the wrong podcast when I asked that?
We
Both.
can talk about it, but I'm not sure. I'm not sure. Maybe half of our listeners would agree with us, and the other half wouldn't agree. So I prefer to talk about math. We have our opinions and they agree about the results among us. So, but let's talk about math. I rather prefer math other politics.
Yeah, well, for sure, 100%. I was just, poking you guys to see your response. Cool. So to our listeners, happy that you're back. Today we have an interesting paper titled A Stochastic Approximation Method, co-title by Herbert, Robbins, and Sutton Monro. And it's from 1951. So some motivation why we're doing this one. So many people claim and cite this paper as the origins of the SGD, stochastic gradient descent. And as practitioners, you all know we use it all the time. And in our podcast, this is like the first paper I can say that goes into the area of optimization, right? So we all agree that data science, a big part of it is optimization. So for sure, we should cover some seminal papers in that direction. So this is the first one, and it was interesting. So previous episode, we had a lot of verbiage. So the ratio between words and numbers was high. This paper is the opposite, right?
Yeah.
There's more, I guess, almost more equations than words.
Yeah, high SNR regime.
Yeah, I hope that our listeners are okay with the high variance between our episodes, because the difference between this episode and the past one gonna be quite significant.
Okay, we'll do our best to convey the math. It won't be easy. And there is so 5 chapters to this paper. We're gonna go one by one. One of them is high on math, so I don't think we're gonna cover it. I just try to explain their motivation. And I have a question for you. So, Nir, what are your thoughts on the paper after reading it, like high level?
Yeah, so first of all, it's a very nice paper. Most of the paper is devoted to show in closed form the convergence under certain conditions of this stochastic iterative method for finding a root of a function or for optimizing a function. That's what we call it today, optimization. And it's a great paper. It goes into estimation, statistics, optimization, and pure math, even as far as I can see. However, and I have to say, however, here, I am not sure that I would call it the first paper that presented the stochastic gradient descent, because for 2 main reasons. First, there is no gradient descent in this paper, period. And second, this paper does not go into detail of how to execute the optimization, but more details of convergence to the solution, or to the root of m of x that we see here in equation 1. And that's just my thought. I mean, it can definitely spark an idea. Let's take this and borrow it and use it in a stochastic way in the gradient method, but it's not very clear from this paper that that is the main approach that we should take. If I'm borrowing this paper and trying to project it into the gradient descent method. So that's just my opinion, I guess.
Yeah. Okay, cool. Mike, what do you say?
I tend to agree with Nir, and I think that the name of this paper contains the word stochastic, and the stochastic gradient descent also contains the word stochastic. So we have stochasticity in both methods, but we don't have gradients here. Okay, we have some problem which we can frame as an optimization problem. For example, it doesn't have to be m of x is equal to some, is it alpha or lambda?
Yeah, alpha.
Alpha. If you are looking for extremo, for example, let's assume that we have some convex function, and we want to find the extremum of the maximum of or minimum concave or convex, this function. So we can rephrase this equation as the derivative of this function is equal to 0, and then they are in the same framework as this paper is talking about. Okay, so in this context, they can think about this problem as some beginning of some optimization of some functions. But as Nir already said, there is no, I don't remember that I've seen gradient here. So it is some stochastic, some function optimization, but without gradient. So it is, it is a semi-gradient, semi-stochastic gradient descent.
Cool, cool. Good points. And soon I'll read the summary, which is like the abstract of the paper, so the listeners could understand more. But I would say something in defense of the paper, that we need to take it into context of the time it was written, right? 1951. So back then, again, almost no computers, maybe really basic ones. So just the idea of iteratively, approximate something was new, right? So we should take that into account. Okay, so read the first chapter is summary, which is like an abstract. They say, let m of x denote the expected value at level x of the response to a certain experiment. So it's a function, m of x. M of x is assumed to be a monotone function of x, but is unknown to the experimenter. Okay, so it doesn't really have access to this function. And it is desired to find the solution, x equals theta, of the equation m x equal alpha. Meaning we want to find x that if we input it into this function m, we'll get alpha. Okay? And alpha is some constant. We give a method for making successive experiments at levels x1, x2, up to xn, in such a way that xn will tend to theta in probability. Okay, so to our listeners, again, we don't have some kind of convex optimization problem. We just want to find, in a sense, the roots of this function m.
Yeah, it's kind of the same, Daniel, because even Newton's method, if you remember, it was focusing on finding roots. We then said, okay, if we want to find roots, we can also find the roots of the derivative, right? And we took it to optimization. But it's kind of the same. But the emphasis here, and that's also something that I don't see any relation from this to the gradient, is method is that he defines m as the expected value. In other words,
we'll get to that. Well, let's wait.
It's in the first chapter. You read it.
Yeah, but mathematically still didn't say it. It's okay. On equation 3.
Right.
Okay, I'm just saying let's not jump and maybe it will confuse people.
Yeah, and Daniel, and small remark about the last statement of the summary. which is talking about xn will tend to theta in probability. There are several kinds of convergence in probability theory. There are some convergence of density functions, and you have almost sure convergence. And as far as I remember, the convergence probability is the weakest type of the convergence, as far as I remember. Okay,
Yes.
I remember for sure that almost sure convergence is stronger than this convergence, and the almost sure convergence mean that this probability 1, the sequence converges to its limit. Here we are talking about something weaker. We are talking about the probability of xn be close enough to theta is going to 0. It is weaker. It is some, it is some bit tough math. I think I studied it 30 years ago, maybe a bit less. But it is I think it is quite important to understand. What we are talking about the weakest convergence here.
Yeah. In estimation theory, we call it consistency, and we've discussed that in one of our papers in this podcast also.
Yeah, probably the first one, the Fisher. We talked about the types.
Fishers. Yeah.
About an estimator. Okay, so let's move chapter number 2. It's called Introduction. So he says, they say, let m of x be a given function and alpha a given constant, such that the equation m of x equals alpha has a unique root, which is x equals theta. As we said, is finding the root, that which number x will give an output of the function to be equal to alpha. And again, this function m, we don't have access to it, as that's the assumption in this paper.
But we can evaluate it. We don't have a formula for it, but we can evaluate it for a given value of x, right?
No, as far as I can tell, we cannot evaluate, because they say here that unknown to the experimenter. Okay. So what you can evaluate is what they define as y. So here, we get to it now.
Some noisy.
Okay.
Noisy.
Exactly. So just to give the motivation, as far as I can understand, they say in real life, like you measure stuff, there's noise. So even if you're trying to measure, I don't know, a height of people, what you're measuring is something else which is noisy, but if you average it out, you get the real thing you're trying to do. So this is equation number 3.
Yeah.
Okay, and that's what Nir alluded to when they say, okay. They say we consider a stochastic generalization of the above problem in which the nature of the function m is unknown to the experimenter. That's exactly the point. Instead, we suppose that to each value x corresponds a random variable y of x with a distribution function that they call it like a conditional probability distribution, h of y given x. So again, we cannot measure the real thing. We measure something noisy, and we have this noise has a noisy thing we measure has a distribution,
like in real life.
Yeah.
But equation 3, by the way, equation 3 is the minimum mean square error estimator, or the posterior mean, as we call it in estimation.
Okay, unpack that, because even for me that was a long sentence with buzzwords.
So when we minimize the mean square error, we get what we call the minimum mean square error estimator, okay, which is a Bayesian estimator, obviously, because this is a posterior density, and dh is the posterior of y given x is a posterior density, and that's called also the posterior mean, which is what algorithms like Kalman filter or other Bayesian approaches do. They find we want to find the posterior mean, which is to say, if we know in advance that some a priori stuff happens with this and this probability, we can, instead of doing maximum likelihood, we can do something even better, which is the posterior mean, which ensures us a minimum mean square error. Okay, that's
so they have an assumption here. So they, in a sense, saying, okay, we're measuring something noisy.
Yep.
Whatever we measure is best estimated by the expectation of this noisy thing, and you're saying that's the MSE whatever.
Exactly.
It's called. Okay, cool.
Yeah.
And Nils, some delicate mathematical question. What about the convergence of this interval? What happens if it doesn't converge? Do we assume it converge?
Yes. So down there, and I think next page, he actually say that the integral between minus c to c on H, on dH, has to be 1.
Finite. 1 even. Okay, I thought
1.
Okay.
So it's not even between minus infinity to infinity. C is a constant. So it has to converge. And he also assumes that M is monotonic. So there are assumptions here.
Okay.
See? There, equation number 4.
And I'd like to emphasize a very small remark that H is not entropy. We've been talking about
I thought about it too.
H is not entropy.
It's not. H is the CDF of Y given X. The
exactly. It's
distribution function.
Yeah. But I thought about it too. It's like 2 years after Shannon's paper.
Yeah. These days we will call it capital F, but he wrote capital H. Yeah.
And they say here, in what follows, we shall give a particular procedure for estimating theta, which is consistent under certain restrictions on the nature of age of this distribution. These restrictions are severe and could not doubt be lightened considerably, so you can for sure make them less strict, but they are often satisfied in practice, as we've seen in section 4. No claim is made that the procedure to be described has any optimum properties that is efficient, but the results indicate at least that the subject of stochastic approximation is likely to be useful and is worthy of further study. Again, let's take it in context with 1951.
By the way, it is interesting that in these old papers that we are talking about, the amount of self-criticism of the authors is much higher than in the modern papers. They are okay, these conditions are very severe, it can be lightened, we don't know how, but they can be lightened. I think stuff like that you see sometimes in the modern papers, but in much smaller amounts than in these papers 80 or 17 years ago.
Yes, 100%. And also, I think it's worth mentioning here that he is talking about. I mean, I see more relations between this and what we do now. For example, in neural networks, even in let's say autoencoder. Sometimes in autoencoder we minimize the mean square error. That's our cost function. When we minimize this cost function, we are searching for the estimator of the mean of the posterior. That's the definition of minimum mean squared error, okay, in statistical sense. When we search that in a stochastic manner, we're basically searching for the root of M. That's exactly what we're doing sometimes in neural networks as well.
Yeah. Thank you for that.
Yeah, by the way, I've just starting to think that it's also related to Bayesian optimization. Yeah. Because in Bayesian optimization for example, for Gaussian optimization, we are trying to approximate this function h by the Gaussian process, and then we are trying to find good hyperparameters of this Gaussian process, and then these hyperparameters help us to choose the next points to evaluate. So I think it is. Then I asked the large language model, what do you think, for which ideas in mathematics it is related? This paper is related. I didn't see there hyperparameter Bayesian optimization, but it is related.
Finding the minimum mean squared error estimator is a Bayesian optimization problem. Period.
Yeah. Go.
No?
So now we're at chapter number 3 or section number 3, and here they provide formal convergence conditions that the sequence, if you follow their algorithm, you converge in probability to this theta. This is quite long, so I recommend just if you have any insight or something special to tell about it, let's do it. Otherwise, we can just skim over it.
No,
right?
just equation 9. Look at equation 9.
Yeah, that's the mean square error, right?
Exactly. Yeah. And if equation 10 is how you, that's the textbook proof, okay, of orthogonality between the errors and the estimator. That's a known property of the mean squared error estimator, and we use to prove that in class we use the smoothing theorem or expectation of the total
Yeah.
expectation law or something like that. Yeah.
Yeah. Yeah, the smoothing. I think it's called, here it is. It's the expected value of the expected value given.
Yeah.
And Daniel, I want to take a look at the equation 7. If you go and you move xn into the right hand side of this formula, you can see something which is a bit similar to what we are doing in stochastic gradient descent or any gradient descent.
Yes.
Because you take the current point and you add into it something, but this something is not gradient, and this is the main reason we stated that we don't know how it is connected. The connection to the stochastic gradient descent, it somehow exists, but it is not very trivial.
Okay, I'll tell it just to the listeners, right? They cannot see it.
Yeah.
So maybe, Mike, you say the equation, describe it.
Yeah, we have an equation of x n plus 1, which equals to xn plus something. And what we have in stochastic gradient descent, we have xn plus 1 equals to xn. In neural networks, we call it theta or w, and there are weights of our neural nets. But here we have the same sum. Xn plus 1 is equal xn plus something, but something is that we see here in this equation number 7 is not gradient, and then because of this we can't tell that this paper is straightforwardly related to stochastic gradient descent. There are some connections and maybe some aspiration to stochastic gradient descent, but it is not so straightforward. Okay,
it is a difference, right? So their gradient, again, it's not a gradient, it's just a difference. They say take the alpha you want to get to, so that's your goal.
Yeah.
Subtract the current yn, so the current measurement at the nth number n step. So do the difference between them and times it by a coefficient, an, that is, they say that is decaying, right? So the larger n decays faster. So they have some kind of, again, it's not a gradient, but it is a difference.
Yeah.
Measure.
Daniel, I've just realized that it can be interpreted as something which somehow approximates gradient. I think if we frame this problem of finding the root of this equation as an optimization problem for the derivative of this function m, I think that an is a learning rate, and the lambda minus yn is just some approximation.
Yeah, that's what I mean.
All derivative. Yeah, it's just what you said. I'm just trying to put it, making it a bit more mathematical. Yeah. So this is something which is similar. I realized just now.
Yeah, they have weight decay. This coefficient decays.
Yeah, absolutely. Yeah, it reminds us of it. It's not exactly it. Yeah.
By the way,
perfect. Thank you.
Near the equation 9 about the convergence. Does the convergence in the quadratic sense is it equivalent to the convergence probability? Because I think I managed to forget it.
No, it's not. It's not equivalent.
So this one, this lim of n going to infinity of bn is equal to 0. Well, bn
Yeah.
is a mean of xn minus this theta in a squared. It is not equivalent to the convergence probability.
But they say so. They say
they prove that it is equivalent if bn is decaying. Yes. If
in this case.
yeah, and if an and bn are decaying, then yes. That's what they prove here. That's what they prove here.
to our listeners, bn is the error between our measurement and the true value we're trying to achieve, the mean square error.
Yep, that's the mean squared error. Yeah, exactly.
Yeah, and I'll give him one more explanation about it. Bn is a mean square error of xn minus theta squared, mean square error, and then from the statement that bn, the limit of bn, then n goes to infinity is equal to 0, they prove under some conditions and on an that it implies a convergence in probability of xn to theta. In general case, I guess it is not correct.
I hope so that you're right, because again, they have like 3 pages of derivations, which we won't go into in depth. Maybe at the end, let's see when they try to summarize it. No, they just move to the next chapter. Okay, but again, to our listeners, the point here is like the update function of how you update the next step in this algorithm is similar to gradient descent, but it's not a real gradient. That's like the summary up till now. Now they say chapter or section number 4 is titled Estimation of a Quantile Using Response, Non-Response Data. So again, using binary data. So they give here like a sub-problem. And can you explain to the listeners what's a quantile, Neil?
The quantile is the ratio, is the amount of times that you get a result out of all the measurements.
Yeah, it's like the value that gives you this ratio, right?
Yes.
So and the median is the 50% quantile, right?
Yes.
It's the number that will give you 50% of the distribution.
Yeah.
Cool. So they try to estimate this quantile using binary outcomes. So they say these measurements now, they're not just any function, like we had prior. Now it could be binary outcome. So when I measure something, I either have a response or I have a no response.
Yeah.
So maybe you can claim this relates to some kind of reinforcement learning when you try to optimize and you have binary rewards, maybe.
This is a Bernoulli trial.
But I think you want to find the minimal value of Zn, which gives you 1. Because if you are overshooting, you will get 1. If you undershooting, you will get 0. So I think you need to somehow, if I understand it correctly, to find the minimal value which brings this function to be 1. I'm not sure. I'm not sure.
Again, they use the same rule.
Yep.
That's previously, right?
Can you scroll up a bit, Daniel?
Yeah.
Again, he says here in between number 43 and 44 equations, he say that this sometimes happens in practice, and in brackets he say bioassay sensitivity data. And if you remember, in one of our podcasts, we've seen the term bioassay to
the second logit function.
Yes.
Exactly, where they try to predict how far can we up the dosage of a drug before we start ruining you completely or killing the killing the drug,
the person.
the medicine, the patient, and that's
And it's a binary outcome. Either you're dead or alive.
yes, and that's how you estimate it. And he shows this as an example.
Yeah. So you have some dangerous pill, this dangerous pill cures some disease, but if this pill is too big, together with the disease, it kills the person. So you want to minimize it. Yeah, it is the same problem.
Yeah, this is exactly, by the way, it's relevant for our days. So I know from personal experience in my family, not specifically me, that the way they treat cancer is they will inject in some way into the body what they call chemotherapy, which is a poison, okay? And they inject it in a manner that is killing all the reproducible cells, including hair cells, blood, red and white blood cells, and including the cancer, which reproduces fast. But they limit the dosage such that the probability of the cancer patient dying from it is as low as possible.
Yeah.
Okay.
And I hope that this dosage takes into account some unique features of a person, the age,
of course,
weight, and yeah.
Of course, but who does these optimization problems for doctors? They don't do it themselves. They have biostatisticians that are doing this stuff.
I hope that not LLMs.
I don't think so, no.
Every product that Mike is gonna work in the future will have like a caveat. We didn't use LLMs during development.
I hope so too. Yeah.
Okay, so let's move to our last chapter number 5, and they say here a more general regression problem. That's the title of the chapter. And they say here, it is clear that the problem of section 4, the binary outcome one, is a special case of a more general regression problem. In fact, using the notation of section 2, consider any random variable y, it's the noisy measurement, which is associated with an observable value x, in such a way that the conditional distribution function of y for fixed x is the function h we talked about prior. The function m of x is then the regression of y on x. Again, to our listeners, think about it as we're trying to fit some unknown function given our data points. Okay, a regression problem. And they say usually regression problem is given by m of x equals b0 plus b1 times x, so like a linear regression. And then you want to estimate the parameters, the beta 0 and 1. They say on the basis of your observations, etc. And they say the method of least squares, for example, yields the estimators bi, or the coefficients, which minimize the expression. And you have here the error between your model, the regression, and the actual measurements. And this is the important part of the chapter, or in the section. They say instead of trying to estimate the parameters of bi, again, some kind of coefficients of your model, under the assumption that m of x is a linear function of x, we may try to estimate the value theta such that m of theta equals alpha, where alpha is a given, without any assumption about the 4 of m of x. Okay, and here they say this indicates that a distribution-free sequential system of making observation, such as given by 7, I don't remember what it is worth investigating from the practical point of view in regression problems. Okay, so I think this is an important point. They're saying here, let's tackle problems in a way that is non-parametric.
Yeah.
Okay, because we don't make any assumptions. We talked about Gaussian, whatever. No, we don't gonna assume anything about the data. We have here a method that is non-parametric. And again, I'm not an expert on the history of statistics, but maybe that was one of the first ideas that introduced non-parametric methods.
By the way, Guy, the formula number 7 is the formula which is the most similar to the gradient descent. They have xn plus 1 equal to x. I talked about this formula. So we have here xn plus 1 is equal to the sum of xn and some learning rate multiplied by the kind of approximation of the derivative. So it turns out that this formula is kind of the most important formula of this paper. They had this theorem, and this theorem is very important. But we are talking about machine learning, data science, and interrelational mathematics, and I think this formula is the main relation of this paper with the stuff.
I agree. So you're converted, Mike. Now you think it is important?
It is somehow related. Then we were talking about it. I started to think that it is also related to so-called Langevin dynamics. When you in Langevin
reminds me of physics.
It is a physical concept, but it's also a mathematical concept. It is a method to generate data from some unknown distribution. You have some data set, and you are generating in the very similar way to this formula, but instead of xn plus some learning rate multiplied by some approximation of the derivative, we have learning rate multiplied by some logarithm of this this conditional probability function. So it is quite complicated, but it is the same. The approach is very similar. You are trying to iteratively get to the good region, and here good region is defined as a region which is close to the solution of our equation. And in the Langevin dynamics, the good regions is the regions in this probability mass. Most of the probability mass is located. So then I look at this formula. I also remember Langevin dynamics, which is a very popular method. It is also related to diffusion models and score-based
and Markov chains, right? And Markov chain models.
I don't remember as for Markov chains, but score-based models is some generalization of Langevin dynamics, and score models is a way to interpret diffusion, generative diffusion model. I think in some episode, maybe in a year or less, we will talk about it.
578.
No, I don't think it will take too much time. But we have to talk about diffusion models, and we talk about diffusion models. We have to talk about Langevin dynamics and score-based models and stuff like that. And then
Noted.
I hope we will remember this paper.
Cool. So Nir, are you converted? Assuming you weren't a believer at the beginning regarding the paper, I mean.
No, I said that you can draw ideas from it to gradient descent, but gradient descent is that we use right now is parametric. You calculate
that's exactly that's what you say. Yeah,
calculate the derivative of a function that you parameterize with all the millions of parameters that we stick into it. So it is parameterized, and at least in the modern sense of gradient descent. So yes, I agree with Mike. This equation 7 is important, and he's reminding us of it. Maybe you can draw and say, okay, let's apply the same method of not using the whole data, but using it chunks by chunks or one by one to other methods and call it stochastic. But this paper is not, I wouldn't title it the stochastic gradient descent method, okay?
Yeah.
I think that it is more related to generative ML, generative method, because in generative methods, yeah, we are also optimizing by some parameters, and then when we are trying to solve Langevin dynamics, we have some the probability function is parameterized, and we are trying to optimize these probability functions, but still with the way we proceed, where we proceed in not in the parametric space, we proceed in the our data space. And here, so it is for me. I just realized that it is more similar to generative modeling, and in particular to Langevin dynamics and its generalization, than for plain SGD. By the way, as far as I remember, in Langevin dynamics, I think we are talking about AN, these learning rates, how to choose them. It is a quite important point how you choose it correctly. So it is not so trivial. So maybe I don't remember. Maybe I see something about Robbins Monro in these papers about Langevin dynamics. But let's get to these papers and then we'll discuss it.
That will be our last paper for the podcast. Then we close the podcast.
Last paper will be AGI or whatever. I don't know.
Yeah.
Last paper is us replaced by AIs or something.
Yeah, last paper, we will not be here. We will be replaced by AI, and they will do the podcast.
Yes. From three persons, from three different persons.
Exactly.
He will complicate all of us.
Yeah, including this beautiful beard.
I think this is the easiest part, The AI already knows how to do it, but still, there are many capabilities which are really far from the intelligence in what is called artificial intelligence.
Yes.
Amazing. Okay, that was a great ending and hopefully optimistic one. I'm not sure. Depends on your views. So I wish everyone a great week and see you next time.
Bye-bye.
Bye.
Bye.